All right. Any questions on solubility? It's an important topic, something that can be a little bit tricky sometimes. Once again, it's qualitative guidelines, somewhat arbitrary in terms of what we consider soluble and insoluble, but we're going to use whatever our textbook is providing as their cutoff. Keep in mind, we talk about solubility of something, we're talking about it, pairing up with something else. We say that nitrate is very soluble because there's no pairs. There's no cations that bind to nitrate that cause a precipitate. Okay, you don't think about solubility in terms of just an individual ion. You think about it in terms of a pair. So we say nitrate is very soluble because there are really no pairs that cause it to precipitate. Binds very weakly to anything. And then we say things like, phosphates are pretty insoluble. Why? Well, because they have a lot of pairs that will precipitate out with them. There's phosphate down here. I just chose phosphate and nitrate because they're both important in terms of environmental chemistry, nutrients and pollution, eutrophication, all that kind of stuff. It's kind of what we're doing in my environmental chem class right now. So keep in mind, it's always about what it has to pair with. So something that's very low solubility just means it has a lot of things that are typically found in water that it can precipitate out with. All right, that makes sense? All right, so does a precipitate form when sodium chloride is mixed with silver nitrate? If so, write the net ion equation for the formation of the precipitate. Take a minute or so to kind of scratch this out. Obviously, you all know what sodium chloride is. You should know what silver nitrate is by now. We had said that silver basically has only one charge, typically one oxidation state, that's +1. So what you basically do is you swap partners, right? And then decide if one of those new compounds formed is going to be insoluble based on your solubility guidelines. Anybody? Silver chloride would be correct. That's right. So what we're going to do is simply write, and you could start with a molecular equation. That's the easiest way to do it. Sodium chloride. You don't have to go, once you get good at this, you don't have to go through all this. Let me just swap the two and write them out, but I'm going to do it just to show you so you get familiar with this. Appropriately, this should be aqueous, sodium chloride plus silver nitrate. And we're going to just swap partners and say we get sodium nitrate plus silver chloride. And then you basically look at your solubility guidelines, you know right off the bat, all group 1 metals are soluble and also all nitrates are soluble. So that's going to be aqueous. And you say, oh, chlorides are pretty much soluble, but one of the exceptions is silver. Right? So that's your solid precipitate. And this is actually a way you can actually measure the amount of something's in solution. So for instance, there's an exercise in your book that I probably told you to do on the outline, and you should do it. Let me double check and make sure I did tell you to do it. 812. To determine the concentration of chloride ion, this is on page 363 in a 100 ml sample of groundwater. A chemist adds a large enough volume of solution of silver nitrate to precipitate all the chloride ions as silver chloride. The mass of the resulting precipitate is 71.7 milligrams. What is the chloride ion concentration in the sample in milligrams per liter? So it's a simple mass type of calculation, molar mass type calculation that can be done to calculate how much of the ion was originally in solution. So make sure you look at that this weekend. If there's questions on it, then we'll talk about it on Tuesday. But that's a way in which you can calculate out a particular substance. Simple to do too. You don't need any sort of fancy instrumentation, right? Something you can do in the field. You can grab a beaker of water, you can add the stuff. You do have to have some sort of mass determination to do that. Oops, I guess I had it written out like that. So there, so to finish our net ionic equation, so if you look at it, oh, why did I write that? Oh, I was just showing, yeah. So I just showed that the two ions, what happens, the ions ionize. You get that. Maybe that's all I was showing. I don't know. Slide won't advance, yeah. So I was just showing that those ions go into solution. They're both very soluble. If you look at your solubility guidelines, of course, nitrates are soluble, sodium chloride. So those are all going to be ions in solution. So ultimately, your net ionic equation then is just silver ions plus chloride ions gives you the silver chloride once you cancel everything out. Okay. Now, there's something called a supersaturated solution. Solution contains the maximum concentration of solute possible at a given temperature is called a saturated solution. That's also known as the solubility of the compound. There's a maximum amount of sodium chloride I can dissolve in solution before the point where if I add more sodium chloride, it's just going to fall to the bottom of the beaker. The solution is saturated. So it's like having a high amount of water vapor in the atmosphere. Eventually it's going to rain. Sometimes you can have a supersaturated atmosphere. You hear that term too. Atmosphere is supersaturated. It's not raining. Why isn't it raining? If you've got this, you're beyond the solubility limit. How do you make, another question, it's the same type of question. How do you make a supersaturated solution? How can you get something that has more than what the solution can hold? Raise the temperature. That's the key, right? Because solubility changes with temperature. For most salts, most inorganic compounds, the solubility increases with increasing temperature. And really for most organic compounds too. And that is the solubility of sugar, right? Increases. When the tea is warmer, you can put more sugar into it than when it's colder. Salts increase. Not always. Most of the things in this class are general guidelines. There's exceptions to that. There's some salts that behave weird and actually their solubility decreases with increasing temperature. There's lots of things going on there, but in general, solubility of solids increases with increasing temperature. Now, gases, that's not the case. The solubility of gases decreases with increasing temperature. We haven't covered gases yet, and we'll talk about that, but with the gas, higher the temperature, the gas molecules get a little bit more energy and they can escape the liquid. And that we'll see the next chapter is actually gases. So what we'll do, what Andrew said, is we'll take our beaker, we'll warm it up, add, so we'll just say sodium chloride, okay? And then if we allow the temperature to slowly cool, and we've added more than what that lower temperatures, let's say we heat it up to 50 degrees C, and we're going to let it cool to 25 degrees C. And at 50 degrees C, we're going to put more sodium chloride than the water holds at 25 degrees C. We allow it to cool back down to 25 degrees C. And as long as you do it slow enough, it'll stay in solution. That's what we call supersaturated. Then all you have to do is drop a little tiny crystal in there of sodium chloride, and all of a sudden it'll fall out of solution. And some of them form nice little, this is like probably like, I think it's aluminum nitrate, forms these nice crystals like this. Same thing with seeding clouds. That's why we seed clouds. You're providing basically what's called like nucleation sites for the water particles to come together on, form that critical mass, and fall out of solution, which gives you the rain. So what you're doing is kind of encouraging rain because you've got this heavily saturated atmosphere, but it's just not raining and you want it to rain. So it's the same thing here. You can have a supersaturated solution, drop a little crystal in there, and it'll fall out of solution. Questions? Okay. All right, that brings us to the last major section of the chapter, and that is the oxidation reduction reactions. Now, this is important because you will see this again in Gen Chem 2. It's the very last chapter, and it's a really important concept. I mean, I hit this stuff all the time in my advanced classes, and my students typically look at me like I'm from another planet. Like, are you mean to tell me you never covered this in Gen Chem? Yeah, they covered it, but they covered it 3 years ago, and they just don't remember it. If you do a lot of cramming, you won't remember stuff. If you study a lot, slowly over time, rather than cramming, the information stays with you longer. But your brain's pretty efficient machine, and if you've been exposed to it, you'll kind of learn it quicker. The second time, you'll remember it and start to relearn it really quick. It's one of the great things about graduate school. You kind of like remember everything you did as an undergraduate and you build on top of that. So oxidation reduction, as I mentioned before, is a transfer of electrons, and it's a super broad class of chemical reactions. So an oxidation reaction is one that increases the oxygen content of a substance. However, that definition is incomplete because there are reactions in which oxygen is not even involved, and it's still an oxidation reduction. And we say oxidation reduction because they go hand in hand. You can't have an oxidation without a reduction. You can't have a reduction without an oxidation. And you'll understand that why as we move on to the second definition. It results in the loss of electrons from an element. Well, those electrons have to go somewhere, right? We're not just flying around. We said that before, that the only time we have naked charges, for lack of a better word, flying around is in high energy systems like plasmas, stars, and particular lighting, or the old plasma TVs, which are no longer around, unless you got a dinosaur in your, although nowadays technology changes so fast, it doesn't seem that long ago the plasma TVs were big. Unlike tube televisions we had when I was growing up. All right. So we have this loss of an electron, gain of oxygen. The second definition is the best because it applies to all oxidation reduction reactions. There's ones in which, like I said, you won't even see oxygen in them. It'd still be an oxidation reduction reaction. So explain to me what's going on here. What's losing electrons here? It says results in a loss of electrons of an element. What's losing electrons? No idea. Well, let's think about iron and oxygen. What? How do you know?
Because the oxidation number on the left is 0, and then it goes to negative. I was -2, so that would be +2.
I'm getting there, but not quite.
Okay.
You corrected yourself. First you said it's going to be negative, and now you're saying it's plus. It's going to be plus because it's losing electrons, right?
Yeah.
No, you're not. You're getting there. I'm sitting here trying to think of your name. Actually, don't tell me for a second, because I know it's it's like the girl in the other class is. Gee, it's what's your name again? Talia. Well, hers is, she goes by Tia, but I forget, it's something like that. All right, Talia's right, the iron on the left is 0. How does she know it's 0? Well, it's just the element iron. So it has 26 protons and 26 electrons. So its charge is 0, right? Right? It's just the element iron. So anytime you see this here, that's the element, iron. You've got a big hunk of iron. Okay, over here, it's part of a compound. It's bound to oxygen. It's not the element iron. The element iron is, how do I say this? It's not the pure element. The element's in that compound, but it's not the element anymore because it's lost electrons. It's a cation, if you will, right? This is like sodium chloride, right? An ionic compound. We use that general definition now, even though we've learned that if the electronegativity differences aren't really that great, and it's not truly ionic, right? We'll say it's a compound that has a metal and a non-metal, so that metal typically loses its electrons. That's what metals do, right? Have you ever seen me write this on the board? Or this? No, they're always cations, right? Metals don't pick up electrons. They lose electrons. So when you find them in a water sample, they're going to be as cations, either precipitated or free ions in solution, right? They're not going to be ever negatively charged. Okay, so we have this iron oxide on the right, right? And people are trying to struggle to figure out the charge. Well, one of the rules that we'll learn here, which is right here, this is what Talia was probably thinking of as she was going through it in her head. She said the oxygen's -2. That's the general rule. It's not always, but in general, it's -2. How do you know that? Well, it's in group 6, right? Picks up 2 electrons, likes to form that octet, right? So it's going to pick up its 2 electrons. That's what oxygen likes to do. Pick up 2 electrons, complete that octet. There are some cases where it's not -2. I'm not worried about you learning the exceptions right now. I'm just going to tell you it's in peroxides typically. Things like hydrogen peroxide and those other metal peroxides, things like that. It's -1, not -2. Don't worry about that for now. You'll learn that later. I think it even says it here. Yeah, there's the peroxide there. Yes, fluorine also. And there's your metal superoxides too. So there's just some exceptions. But don't worry about those for this Gen Chem 1. You might need to know them for Gen Chem 2. So that means if the oxygen is -2, what's the charge on iron here? What? Plus what? +2, +3, right? How are we getting that? How are they getting this +3? Right, very good, Abigail. So what we're looking at here is, we could write it out almost like a mathematical equation here. You say the total charge on the compound, there's no charge up here, so this thing is 0. Just like an element. If there was a charge, we'd write it up there, right? Just like when I write sulfate. That has a -2 charge. There's no charge written. This is just a neutral compound, right? So that means the total charge, I'll put a T, is 0. And that's equal to the charge on the oxygens plus the charges on the irons. Well, there's 2 irons, right? And there's 3 oxygens. And the oxygens we said are -2. So I'm doing just what Abigail said out loud a second ago. Well, there's 3 oxygens, each at -2, that's -6, right? So the total iron has to be +6, and there's 2 of them, so each one is 3+. That's how you determine the oxidation state on the iron here.
Can you not just get that from the Fe2O3?
Yes, you could. So you could, well, it's the same thing effectively. Oh, I see what you're saying. Yes. So very good. So Fe2O3, we know is, from our reverse process like this, is iron 3. So Houston's right there. You could do it just like that. That won't work for substances like this. So that's why I do it like this. And that's why I started doing it like that. But she's right. With the inorganic compound, basically, boom, you already know that rule. You bring them down and cross them like that, right? So you can work backwards like that. This is the foolproof way when you deal with substances that are not inorganic and ionic, things like all of your carbon compounds, which is still all your combustion reactions. These are all oxidation reductions also, okay? So is everybody comfortable with how we got the charge on iron there this way so that you can do that in the future for anything? Okay, and what you're doing is you're following these rules. And of course, once again, you don't have to memorize. However, keep in mind, the final exam is not open book, open note. You should have gotten an email or it's going to come around soon from Dr. Friedman. So be on the lookout for that. There's a separate website set up that you'll be able to visit that'll have like the review sheet and all that. The exam will be on campus in a different room than this so that we can all spread out. And I will be there proctoring it, but you'll be spread out. It will be on D2L, so you'll still be using the D2L, and you'll be able to, he'll have a nice handout sheet that's going to have things like this. That, you don't have to memorize that. You'll have all your constants and equations. You have to memorize equations, okay? But you won't have, you know, Vesper there in front of you and say, oh yeah, 5 pairs, 2 pairs is, you know, that stuff you'll have to start to commit to memory. Okay. It's one disadvantage of me using open book, open note. I think it's the last year we're using a common final. So after this, I'll be able to give my final the way I want to give it.
Quick question on the final, will the molecular trace be something you use for memory?
Yeah, because that's definitely going to be on the final. And it's not hard. You just make up a little index card to study with, not to take to the exam. Stick it in your sock, your take an index card, write them up with the pairs and the names, and learn them. And to be honest with you, final exams cover a lot of material, and they tend to stick to more basic, fundamental stuff. So. But the Vesper is a little tricky, but even the other stuff, you tend to focus on the major concepts from that chapter rather than the more extraneous stuff. You only have an hour, yeah. You're used to 85 minutes, right? 25 to 30 questions, yeah. It's maybe a little bit longer than mine with less time and no open book, open note. Which will be fun. All right, so you've got these guidelines. It basically says 0 for atoms and pure elements. That's what we said here. Iron is 0 here, right? And we said this is +3 now. Let me do this actually. 0 for the iron. Here it's +3+, right? So that's the oxidation. We didn't finish. Something has to be reduced. Well, there's only one other thing left, oxygen, right? Okay, this is an easy reaction because you've only got 2 things. So the oxygen's reduced. So what's the charge on the left for oxygen? 0, because that's elemental oxygen. That's the way oxygen is formed elementally as a diatoms, so it's 0. So Hershey's right there with that being 0. So what's it on the right? We already decided that, -2. We already know that.
I thought you were asking.
No, I'm sorry. Yeah, I was asking on the left. Maybe I said, yeah. So it goes from 0 to -2. So that means it's 6 electrons are being transferred, right? Because we have, oh no, I'm sorry, 12 electrons are being transferred, right? You got 4 iron, each going from 0 to +3. So 12 electrons are being transferred, and then we have 6 oxygen, each going from 0 to -2. We have a total of 12 electrons being transferred from the irons to the oxygens. The oxidation number, the charge of a single atom. So that just means this. The oxidation number on sodium is +1. The oxidation number is, it's kind of like the charge on things like this but it's the theoretical charge in compounds. So theoretically, this is the charge on iron because it's the less electronegative element and it gives up its electrons. So it has this theoretical +3 charge in that compound, right? We can do the same thing down here. We're going to do it. Those are a little bit different because here you realize these are ionic compounds and you say, yeah, that has a charge. That's what an ionic compound is, right? Cations and anions are attracting each other. That's not what CO2 is. How does that have a charge? Well, there it becomes more of a theoretical charge based on differences in electronegativity. Okay? And it's a way to just keep track of the electrons. It's kind of like an accounting scheme to figure out how many electrons are being transferred, what's being oxidized, what's being reduced. And then you can understand what an oxidizing agent is, a reducing agent. You can pick the appropriate one, understand why cars rust and bridges rust and all of that, and how batteries work. It's all oxidation reduction. Fluorine's -1 pretty much in all compounds. It's the most electronegative element, so that makes sense. It's always going to be the one that grabs the electrons in a compound. And then there's their oxygen -2 we've talked about already with a few exceptions. Oxygen's +1 in nearly all compounds. There's a few exceptions there. Once again, don't worry about exceptions for Gen Chem 1, but you see when it's bound to something like a metal, like lithium hydride there, it actually is -1. The oxidation number values of the atoms in a neutral compound sum to 0. That's what we just said. The oxidation number of this whole thing has got to be 0. All right? There's no charge on it. That's what that's second to last statement is saying. The oxidation number values of the atoms in a polyatomic ion sum to the charge of the ion. So let's go do sulfate. Someone tell me what the charge on sulfur is there. +6. Andrew's right on the money. How did he get that? Well, he said oxygen's -2, and there's 4 of them. That's -8. -8, and what gives you -2? +6. What group is sulfur in? 16 or 6, depending which periodic table, right? 6 valence electrons. Shouldn't be surprising to you that it loses 1, 2, 3, 4, 5, 6, all of its electrons when it's bound to something more electronegative, right? Another common charge of sulfur is what? What is it here? What? -2. You caught your mistake. Very good. -2. Why? Well, it's in group 6, just like oxygen. What did we tell you all along? Things in the same group do the same type of things, right? Oxygen's often -2. Sulfur's often -2. Why? Gets its octet. Why is it -2 here and +6 here? Well, it's bound to a strong electronegative element here. Here it's bound to a weaker electronegative element. So here it's -2, here it's +6. Does that make sense? Assign oxidation numbers to each element in the following compounds. The first 2 are provided as examples. Nah, let's not provide them as examples. Let's just do them. What's sulfur there? That's easy. That's 4, right? You got 2 oxygens. That's it. Now, the other thing I want you to realize is that's this right here, +6. That's the highest oxidation state for sulfur. You're not going to see it more than 6+. Why? Well, it's lost all 6 of its valence electrons. It's the most oxidized form of sulfur. It also is bound to 4 oxygens. The other definition of oxidation is the oxygen content. So if you see it from both ways, you pick up on it real quickly. That's a heavily oxidized form of sulfur. You can see it right off the bat because it's got 4 oxygens. And then when you calculate the number, you realize, hey, that's the most oxidized state of sulfur. So it really can't lose any more than 6 electrons. Then you're talking about losing them from that inner shell. Forget that, energy-wise, it's not going to happen. You'd have to lose a 7th electron from the core electrons. There's just nothing out there that's going to do that. 2 sulfur. So we said sulfur's 4+, oxygen obviously is 2-. The chromate ion here. Very good. Houston's got it, 6 plus. Same thing we always did. We say the total charge is -2. That's equal to the sum of the chromium plus the oxygen. And the oxygen we know is -2, and there's 4 of them. That's -8. -8 and +6 gives me -2. Chromium, look where it is. Oh, geez, surprise. It lost 6 electrons. 1, 2, 3, 4, 5, 6. It's 4 in its D, it's 2 in its S. That is a common oxidation state of chromium. It's not the most common one, but it is. That's the one that's toxic. That's the one that's got carcinogenic properties to it. That's the one that was famous from the Aaron Brockovich case. You remember that one? I don't know if you remember, you weren't alive, but I forget what year it was, but anyway, it's pretty famous. You might have heard it, even after the fact. It was hexavalent chromium that was causing all the problems in the water supply, getting people sick in this town that she brought kind of to light. All right, what's the charges on the nitrogen and hydrogen there? Flip there. Yeah, nitrogen, hydrogen is always +1 except for when bound to a metal. So it's going to be +1 to hydrogen. That's the rule, except when it's bound to a metal, right? Hydrogen's +1 right here. Right? And it's in group 1, just like the other, no, I shouldn't say the other metals, because it's not a metal. The alkali metals are all +1. Lithium, sodium, hydrogen falls. That's why hydrogen, I always say, schizophrenic. It's over here because it's +1, but then it's over there because it's a non-metal. And then it forms a -1, so it's over there. So hydrogen's the one weird one. Okay, so now we say hydrogen's +1, and nitrogen's going to be -3. So is that a reduced form of hydrogen? I mean, hydrogen. Is that a reduced form of nitrogen? Yes, right? Here's the other definition. Reduction, reaction that decreases the oxygen content of substance. I'm going to put increases hydrogen content. Reduction often is an increase in hydrogen content. And it makes sense because hydrogen's +1, so that's going to make the other element negative, which is what reduction is. Some people get confused by this term. I've had that question before. Dr. D, why they call it reduction? It's gaining electrons. Gain a reduction? It's a reduction in the oxidation number. That's where that word comes from. We're talking about the oxidation number. So it's a reduction in the oxidation number. So oxygen got reduced from 0 to -2. Reduction. Okay, don't think about the electrons, that'll confuse you. It's the gain of electrons. ClO3 minus, chlorate. Very good. Oh, plus, no. 5. Yeah, it is 7 sometimes. That's why I was like, well, chlorine is actually 7 sometimes when you have this, the perchlorate. It's 7. This one, it's 5, right? Abigail kind of caught her mistake as Houston said it. Oxygen's -2, so there's 3 of those. That's the -6, and we have to have a -1 charge, so that means chlorine's going to be +5. Chlorine's a finicky one. It can lose all those electrons, but it can just lose the 1, 2, 3, 4, 5 in the S, right? That should make sense to you. I mean the P. I said S, P. The 5p electrons still got its 2s. That should make sense to you. Or it can lose all 7. Those are common. It makes sense to you from a quantum theory perspective of electron configurations. SF6. What's sulfur there? Positive 6 again, right? Carter, right? I knew his name and I kind of drew a blank. Carter's right with +6. What about the last one, chlorine? 0, that's elemental chlorine. Everybody comfortable with how we got +6 here? Just fluorine's always -1. There's 6 of them. That's all. And then that's elemental chlorine, so that will be 0. So anything that's elemental state, so that means the halogens or diatoms. You're also oxygen, nitrogen, hydrogen gas or diatoms. Sulfur, sometimes you will see there's an elemental sulfur of S8. It's actually elemental sulfur. That's one, it's the rhombic form, I believe. I think there's an S2, but don't quote me on that. Sulfur's a little odd. They're all odd. Questions on oxidation numbers? So now that you know oxidation numbers, you can look at a chemical reaction to figure out what's being oxidized and reduced. So in this case, what's the oxidation number on carbon there? 2+, right? +2. Was it on the right? +4. So it got oxidized. Okay. The iron got reduced. You can see that without even figuring out the numbers. We just did the numbers up top, so no big deal. But you can see it's reduced. It's in a compound here, and it's going to 0 there, and the metals don't get less than 0, so that's going to be reduced. But that is the most oxidized form of carbon, CO2. You can see it bound to more oxygens, but it's in an ion, like CO3 2-, where it's still 4. You see, still +4 there, right? And it's +4 here. That's the most oxidized form of carbon. Yeah, it's only got 4 valence electrons. That's what you see. The most reduced form of carbon, can you guess for me what it is? Give me the compound that would tell you the most simplest compound that would make carbon the most reduced. The simplest of hydrocarbons. The other definition says hydrogens, right? Very good. CH4, methane. That's the most reduced form of carbon. It's now gained 4 electrons, right? This is why carbon is such a backbone molecule, because it's in the middle of the periodic table, and it's a non-metal, can form bonds with so many different things. It can take on negative or positive, right? And it can form those 4 bonds. It's a great structural atom. Okay, we can determine which atoms gain and lose electrons by determining oxidation numbers. So here's one without oxygen, but it's very simple, right? Much easier than what we've done already. You got zinc going elemental to zinc 2+. Now, you do reactions in lab, and I forget exactly what you're doing in lab, but this is a reaction that happens. If I take a piece of zinc and put it into a copper sulfate solution, the sulfate's a spectator ion, should have been copper chlorate. Copper sulfate's one of my favorite compounds. Get that beautiful turquoise, almost like yours and yours shirts. What's your name again? Tommy? Tommy and Megan's color. Beautiful. If you ever seen the crystals, it's really pretty. The solution, depending on how concentrated it is, can be really, really deep blue. But this could have been copper sulfate. Copper chloride. We don't care. All we need is the copper. But this happens. If I put a strip of zinc into this solution, the zinc gets oxidized and the copper gets reduced. The reverse reaction does not happen. If I put a piece of copper solid into zinc sulfate solution, nothing happens. Why?
It's not.
Oh, go ahead.
Read her one more time. He doesn't mean it. He doesn't mean it. He doesn't.
you have an answer, or is your mic unsilenced unintentionally? I think that was unintentional. It doesn't ionize. That's not like the correct way of like thinking about this. So, I mean, why does the forward reaction happen? Think about it from electron perspective. What kind of terms do you know that describe what's occurring here? Think about it in terms of electrons. Why is this happening? It's not a trick question. It's incredibly obvious. I just want you to verbalize it. Yes, it does make it more stable. And so effectively, that's why it happens. I've told you that all along. But effectively, you could say that, well, copper likes electrons better than zinc. It has, you could talk about in terms of electron affinity, maybe, or ionization energies, right? Things like that. You could say that, okay, that's the nature of these two, that copper holds on to its electrons, likes electrons more than zinc does. So when I put copper solution, which has lost electrons, in the presence of zinc, which has all of its electrons, it steals them, and this happens. But the reverse doesn't happen because this hangs onto its electrons. Okay, so it's just kind of like verbalizing and visualizing what's happening, kind of, and thinking it through. There's nothing other than that, and your book will talk about a table. Activity series. Does your book do that? Activity series, yes. On page 375, I have a table of activity series. And that's basically what I'm saying here is kind of their electron activity. I like to think about it in terms of reduction tables. Activity series, typically aren't used that much by chemists, but a lot of books introduce them at this point because you won't cover reduction potential tables until you get to Gen Chem 2. Okay, so electrons have been transferred, oxidation numbers were good. Any questions on what's going on here? Yes, Abigail. No. Yeah, no, you don't have to know trends for the transition metals at all because they're fickle. They're up and down depending on the d pairings and electrons and all of that. And remember, electronegativity is for what's going on in a bond, for ionization energy, and electron affinity, or what's going on for like an isolated atom. It's really measured in the gas state, but you can apply it to what's happening for an isolated atom. But electronegativity is really for bonds, what's happening in a bond. They definitely relate, and they correlate to some extent. All right. Based upon the observations of the reaction shown, we conclude that the unbalanced reaction equation is, what is this? This is silver and copper. See, I probably cut out a slide and didn't realize I missed something. But anyway, so let's say we have a reaction now in which over here on the left, we've got silver ions, so silver nitrate and copper solid, and we get a reaction where we get a silver precipitate. It's forming on the wire there. You can see it, right? There's the copper wire. Now you've got this coating on it. That's the silver, elemental silver that's precipitating and coating that. And you get copper ions released, and you see the color changes from the copper ions now that are in solution. So in this case, though, your electrons aren't balanced, right? Because silver is going from +1 to 0, and copper is going from 0 to +2. So electrons aren't balanced. So we actually have to balance it. That's all. Now there's a copper +1. Well, that's a good question. why doesn't copper 1 form here and copper 2 forms? Huh. Note to myself, I'm gonna look that up. Anyway, for this particular reaction, the electrons are not balanced. So we can balance these by following these 5 steps. Write the half reactions. I mean, this is pretty easy just to look at and do. These are the steps that are applied when they get more advanced, and you should follow these steps. We're going to keep it pretty basic here. Depending on who you have in Gen Chem 2, you might be asked to balance redox reactions in acid and base solutions. Some faculty do that, some don't. That's in Gen Chem 2, though. And then these steps would be a little bit more important, and there'll be additional steps, actually. Because you have to balance it with waters and acid and all of that. So you write the separate half reactions, you balance the number of atoms in each, balance the charge in each half reaction, that's by writing the electrons. Multiply each half reaction by the appropriate whole number so the electrons are equal, and add the half reactions together to get the overall redox reaction. So here you go. Write the separate half reactions. Okay, copper goes to copper 2 plus 2 electrons. Silver plus an electron goes to silver. The atoms are already balanced. And the charges are now balanced with these electrons written. That's what this step is here. Is that the -2 and the +2 equals 0, which is equal to the left side of the equation also, 0 over here. That's all that is. It's kind of a fancy way of saying you've kind of like, you're doing what we've talked about already. So, oh, there it is there. I was like, well, something's missing from the slide, the first steps. That was weird the way I've got the animation set up. That didn't show up until afterwards. Okay, so there's my separate half reactions. The number of atoms are already balanced. Then we've got this balancing the charge by adding the 2 electrons here and the 1 there. Then you've got 0 on the left, on the right for the silver and the copper. And then multiply each half reaction by the appropriate whole number so the electrons are equal. So all we're going to do is take the silver one and multiply it by 2. And then you combine them. The electrons cancel out. That's what you're after. You have to have an equal number of electrons because whatever's lost has to be picked up by something. That's the whole point of doing this. And then get your overall reaction. Questions?
For the example, we only have to know how to do it if we don't do it.
Oh yeah, yeah. If I'm not talking about it in class, I'm not responsible for it. Any sort of major topic, that's what I mean. Yeah, so is that even done in this chapter? Or is it done in Gen Chem 2? So I think they used to do it here, and I think they moved it in this new edition, which is good because it was too much for here. Either that or I'm just not remembering correctly. Oh, here it is. Here it is. No, here it is. It's all right here on page 377. Redox reactions in acidic or basic solutions. Do not worry about this. Okay. Sample 819. That's why it's not on my outline for you to do. Okay. Yeah, you can see it can get pretty involved with adding the waters and the base and the acids, all this. Don't worry about that. So here's the copper wire immersed in silver nitrate. Why am I doing this again? Kind of did this already, right? This is what we just did, copper and silver. Electrons must be balanced. All right. So here's the activity series of metals. We can use this series to rank the strength of metals as reducing agents. So A reducing agent is just what the word says. It's an agent that carries out reduction. An oxidizing agent is an agent that carries out oxidation. So oxygen is a great oxidizing agent because it likes to be reduced. Right? Does that make sense? That's the way you have to think about it. Oxygen carries out oxidation. In the process, it becomes reduced. That's what we saw right here. Oxygen got reduced. It oxidized the iron. This is the rusting. It's the rusting of metal. It's the oxidation of metal. That's what rusting is. It's the oxidation of the metal. So oxygen is a great oxidizing agent. It's the one that's ubiquitous. It's everywhere, right? It's pretty strong oxidizing agent. So therefore, it likes to be reduced. So an activity series for metals. You can use this series to rank the strength of metals as reducing agents. The metal cation will oxidize any metal above it in an activity series. So I have to think about this because I don't use this. So what they're saying is that a metal cation will oxidize any metal above it in an activity series. So gold here is, if you will, the best strength of metals reducing agents. The metal cation will oxidize. This is what's confusing. Metal cation will oxidize any metal above it, right? So if I have gold ions in any of these elemental metals, it'll oxidize all of those. Lithium metal will oxidize none of these. So the best this is what's confusing the way they do it. I'm so used to reduction tables. The best reducing agent here is this, because it's the most likely to be oxidized. It's the highest on the table, you see? It's the most lithium metal is the best reducing agent because it's the most likely to be oxidized. You understand why I'm confusing myself? Because this is, if people use reduction tables more prevalently than an activity series is the exact opposite. It's basically an oxidation table. Okay, and people don't use these once you get in advanced chemistry. Everything's reduction tables. So it's effectively it's an oxidation table. So the one the highest on the left is the most likely to be oxidized. The one lowest on the right is the most likely to be reduced because it's the best oxidizing agent. And this is the best reducing agent. It'll take time to digest, and I still catch myself, having to slow myself down and say, wait a second, okay, it's going to be oxidized, it's an oxidizing agent, blah, blah, blah. So silver ions with copper solids is the one we've been looking at. Here's copper, and where's silver? Right below it. So that means silver ions will, right, oxidize the copper. That's what we just said. Just like gold will oxidize any metal above it. So you're talking about this oxidizing any of these elemental metals, and this reducing any of these cations. Questions?
Silver itself is reduced, but it actually oxidizes.
Say that again.
Sorry, the silver itself is reduced in that particular equation, but it acts as the oxidizing agent.
Yes.
Okay.
They always have to be paired. So each one will carry out something, and in the process, the other thing will happen to it. If I carry out an oxidation, I will be reduced. If I carry out a reduction, I will be oxidized. So no reaction here. This is what I was getting at before. Zinc ions with copper. Use a different color here so I can follow this. Zinc, where's zinc? There's zinc ions. And then copper down here, you see? No good, no reaction. Zinc, copper ions with the zinc would have worked, right? With the elemental zinc would have worked, but not the reverse. So the top one has to be on the left, the bottom one has to be on the right. For this, when you get to Gen Chem 2, we'll switch it on you. And it'll be reduction. And from then on, you'll just see reduction potential. You occasionally still see these, but they're just, most people just write out and tabulate reduction potentials. Questions? Okay, let's take a look at this one. What is being oxidized? What's that? No. No. Hence, process of elimination. It's the carbon, just the carbon. Let's take a look at this. Now, what type of reaction is this besides an oxidation reduction, more specifically? Combustion. Combustion is the oxidation of carbon. That's what it is. We just said that CO2 is the most oxidized form of carbon. Hydrogen is always +1. It's +1 here, and it's +1 here. The only time it's not +1 is when it's bound to a metal. And I said you don't have to worry about the exceptions. Right? Carbon. Well, you've got 6 hydrogens, right? So each carbon's 3+, right? And over here, we know already it's 4+. We've done that already. That's CO2. The oxygen's being reduced, same as always, from 0 to -2. It's going to be -2 in all these places. So oxygen's going from 0 to 2-, and there are 14 oxygens, right? 28 electrons. That's something's wrong.
Wait, is it carbon 3-?
Oh, I'm sorry. Yes, thank you. 3-, not 3+. Thank you. 3-. That's the mistake. -3. So we now, I'm just double checking that our electrons balanced, so we can see this. So we've got 28 electrons. There's, what do we got? Just 2 no, 4 carbons. 4 carbons to go from -3 to 4 plus 7 electrons. That's 28 electrons. Very good. So there's 7 electrons being transferred for each carbon, and there's 4 carbons. So that's a total 7 times 4 is 28 electrons. So you see the hydrogen, nothing happens to the hydrogen. It's +1, +1. Right? Always look for carbon. Anytime you see a combustion, it's going to be carbon being oxidized. And oxygen is going to be reduced. O2 is the oxidizing agent and is reduced. The carbon in C2H6 specifically, you could say the C2H6 is being oxidized, specifically the element carbon is being oxidized. C2H6 is the reducing agent. When you talk about the agent, it's the compound. You don't say carbon is the reducing agent. It's C2H6 is the reducing agent. Questions? Using representations A and I think it's supposed to say A through I. Which solids dissolve in water to create solutions that conduct electricity? So we'll start with A. Does A work? Should we choose A? Is that going to conduct electricity? What? Why? Yeah, it's silver nitrate though. It's got no, so the way they're drawing that, let me see what they're doing here. Oh yeah, so there's the silver ions. They're separated from the nitrate ions. There's the nitrate ions, right? That's all they're showing. The rest are water molecules. So they're showing it as dissociated. That's what they're doing here. Silver ions and nitrate ions, because that is a soluble compound. It's just confusing the way the notation is. You see it now?
So it's AG plus, that's what that says.
Yes. Can you not see that? Yeah. Sorry. Yes, there we go. Better? All right. So A, we're choosing definitely, right? B? No, solid copper. That's not going to dissolve in solution. If it does, it's going to be minuscule amounts. And it'll be as a copper atoms, not ions. Oops, I wasn't supposed to circle it. That's bizarre. Oh, it froze. Oh, now we won't be able to get rid of it because I kept it. So just A. How about C? That's copper nitrate. Yeah, we definitely want that. D. No, it's a sugar, right? So it's not going to form any ions. It's going to be sucrose. E. Well, what's it visually showing you? A precipitate, which means it's not going to create a lot of ions in solution, right? That's kind of that point I made before. Anything that does go into solution will form ions, but they won't be appreciable enough to conduct electricity. So they're not considered strong electrolytes. F, of course. G, that's a strong acid, so completely ionized, showing you the ions. Sodium iodide ion. Yes, that's a nice soluble salt. HF. No, that's the one halogen acid that is not strong, remember? So it won't form, all the others are strong. HCl, HBr, HI are all strong acids. HF is not. Small fluorine, small hydrogen, they form a really strong bond. And you get very little ions in solution, so we're not going to choose that one. Something about zooming and then getting the heck out of here. Can't even close it. There we go. Okay, I have a practice problem here we're going to do. And then we got our summary done with the chapter. So, question is, what mass of barium sulfate is produced when 100 mils of 0.1 molar solution of barium chloride is mixed with excess iron 3 sulfate? This is similar to the question I just told you about, A12, with kind of figuring how much chloride was in solution on page Page 363. This is similar. So, what mass of precipitate is going to form? And specifically, barium sulfate. So, I'm not going to ask you to do this on your own. It's a tough problem. So, we're going to actually just talk through it. How do you want to tackle this? Write the equation. Now, it's a common way to start, right? Most times we'll tell you to write the equation, and we can do that. So, what mass of barium is produced when 100 mils of, okay, so we're mixing barium chloride, right? What's the formula for barium chloride? The ACl2, because barium's in group 2, and it's mixed with iron 3 sulfate. What's the formula for that? Fe2 what? That's sulfide, not sulfate. Sulfate is the SO42 minus. Sulfide is S2 minus. So that then, right? That's iron sulfate. Four irons? That's all right. Yeah, so it's iron 3, so we got +6 there, and then we got -6 because sulfate's -2. We good? Now, I forgot your name again. Shakira said, let's write the formula. Barium chloride plus iron sulfate. Swap partners and make sure you get the right formulas. So barium sulfate's going to be what? Formula-wise. BaSO4, right? Because barium's +2, sulfate's -2, so I don't need any additional there. And then you got the iron chloride. It's not balanced. We can balance it. Whoops. That 2 came jacked up. It's kind of a misplaced there. But there should be a 2 in front of the FeCl3 rather than floating on top of it. And I think that's right. That gives us 3 barium, 6 chlorine, 6 chlorine, 2 iron, 2 iron, 3 sulfate, 3 sulfate. By the way, easy way to balance when you got polyatomic ions on both sides, don't break them apart. Balance the sulfate and sulfate. If it's going to be the same, don't worry about balancing sulfur and oxygen. Just keep that as because it's present on both sides, so it's easier. Now, this is all very nice, but you'll realize that you don't even need to do this. Because think about visually what's happening. I've got a 100 ml beaker here of 0.1 molar barium chloride. And I'm going to add a bunch of iron 3 sulfate. How much is going to precipitate? Tell me in just qualitatively how you describe what's going to precipitate. What's controlling it? How much you're going to get? The barium chloride, right? Because that's limited. And specifically the barium. All we care about is the amount of barium, right? That's it. The balancing is the recipe, but this doesn't matter. We're not following the recipe. We're just saying we've got this much barium in solution, we got all this extra sulfate. How much is going to precipitate? Well, just take that amount of barium that's in grams, convert it to moles, mass of A to moles of A, right? Moles of A to moles of B, B being barium sulfate, and that's it. And convert it back to mass. It doesn't matter what the stoichiometry is, right? Do you see that? You don't really need the stoichiometry to do the problem. So, how much barium chloride do I have? I've got 0.1 molar times 100 mils. So I got 0.01 moles of barium, because the moles of barium is the same as the moles of barium chloride. And that's because there's 1 mole of barium in 1 mole of barium chloride. So I didn't kind of like have that step there. You know, I went from barium chloride to barium. Because they're 1-to-1. Just think about, remember what a mole is. It's a number of particles. So just think of it as Legos again. I got one black Lego and 2 yellow Legos. The 2 yellow are the chloride, right? If I've got a dozen, right, of this one black Lego with 2 yellow on it, I got a dozen of those. I still have a dozen of the black, right? That's the 1 mole. That's the same here. So we don't have to worry about doing any sort of anything else. This equals the moles of barium chloride, but it also equals the moles of barium. Does that make sense? And then how did we get the barium sulfate? Well, we started with 0.01, and once again, it's still 1-to-1. 1 barium sulfate for every 1 barium, and that's the molar mass of barium sulfate. So the answer is 2.33 grams. And that it's borne out in stoichiometry that this is a 1-to-1 relationship, right? If we had something like barium phosphate, where there's 2 barium, right, or 3 bariums for every 1 barium phosphate, then you'd have to change these 1-to-1s here, right? And then the stoichiometry, I can't believe that I forgot your name again. Shakira, why? And then Shakira, effectively, this is what you're doing. This is her stoichiometry. And so you can do it this way. And especially if you get something like I said, barium phosphate, oops, 2. Then this isn't 1-to-1 here and here, you see? And then you can do it using stoichiometry, or you can just do it without balancing the reaction, but you got to be able to write the formulas. You got to be able to write barium phosphate, and then you just use that. You don't necessarily have to balance the reaction. You can just use the formulas. Questions? So try that 1 and 2 in your book. I mean, it's solved for you, but there might be one. Anytime I sign the ones that are in the book, there's also ones at the bottom that are unsolved that are similar. So there's a practice one with sulfate. Oh, it looks like very similar to what I just did. Yeah, different numbers, but it's very similar to this one. The practice one. Question. All right, we will call it quits.